Now we're going to start section 4.4, the fundamental theorem of calculus. This one's obviously very important just based on the title. We're using the word fundamental. So think about that and as it applies to everything that we do here. Now, this is not overwhelmingly challenging, okay? We're going to go through Theorem 4.9, but you've done a lot of this in 4.4. A lot of this is really just finding the antiderivative. Before, when we found the antiderivative, right, we had to do a plus c at the end because we didn't know what that constant of integration was. Now that we actually have limits, notice our integral is going from a to b, or we have a specific interval that we're going to be on, we can evaluate that. So, if we look at Theorem 4.9, it says if a function f is continuous on the closed interval a to b, and f is an antiderivative of f on the interval a to b, then we can write it as the integral from a to b of f of x dx equals f of b minus f of a. So we really got to pay attention to the lower and uppercase f's here. Alright, remember the lowercase f is the derivative, or the function that we're going to start out with, and the uppercase f is the antiderivative. So what we're doing when we're solving this integral is we're going to take the antiderivative, evaluate it at the upper limit, and then subtract that from the antiderivative evaluated at the lower limit. So that's really what f of b minus f of a is. So let's just take a look here at a basic example. Alright, I'm not going to spend a lot of time going over the antiderivatives. We did that in section 4.1. So we should have some familiarity about doing that. This section is really just going to give us more practice in being able to actually integrate. So now when we do this integration and find the antiderivative, we are no longer going to use the plus c because we have limits of integration on our integral. So the first step to these is finding the antiderivative. So the antiderivative of x squared is x cubed over 3 minus 3x. Okay, so that's our antiderivative. And then we write this straight line from 1 to 2. That shows that we're going to evaluate the antiderivative at 2 and at 1. And we always do the upper limit minus the lower limit evaluated. So what we're going to do is we're going to take the upper limit, which is 2, and substitute it into the antiderivative. So you're going to have 2 cubed divided by 3 minus 3 times 2. So everywhere there's an x, you're going to substitute in the value of 2. Then minus, over here, the lower limit evaluated. So you're going to have 1 cubed over 3 minus 3 times 1. So everywhere there's an x, you're going to put the lower limit in. And then really it's just a matter of getting through the algebra and substituting in and simplifying. So when we put that in, we're going to get 8/3 minus 6 minus 1/3 minus 3. Alright, so simplify those down. The biggest, most important thing that you have to make sure that you don't make a mistake at is when we subtract these two, that subtraction sign has to distribute to each term in there. That's why it's good to get this down. So if I'm talking about the right hand side here where we have 1/3 minus 3, and we go 1/3 minus 9/3, and that equals negative 8/3. If we can get it down to one function, or one term, sorry is the more correct vocabulary, one term, we have negative 8/3. In front of that's a minus, so remember the signs are going to change there because we have minus a minus, which becomes a plus. So that's where a lot of people tend to have errors, is keeping track of that minus sign as we go through this. So we end up having negative 10/3 plus 8/3, that's going to equal negative 2/3. So we've evaluated what we're calling a definite integral. Definite integral meaning we have limits of integration. Everything that you did in 4.1 was an indefinite integral. So we didn't have limits of integration. We had some sort of constant of integration. We integrated the entire curve. This is where we're going to integrate only a specific interval to get a specific value. So let's just compare the two. So example 2, on the left hand side we have the integral from 0 to 2 of 4x dx, and on the right hand side a totally separate integral, the integral of 4x dx. What we did on the right hand side here is very similar to section 4.1. Notice it's an indefinite integral. There are no limits of integration on that integrand. So we would just take the antiderivative and go plus c. So that's why without limits, so 4.1 is what we're doing on the right hand side here, we get 2x squared plus c. On the left hand side we do have limits. We're going from 0 to 2. So we take the antiderivative, which ends up being what? 2x squared. You should be able to work through that. I showed the steps. And we evaluate 2x squared from 0 to 2. So notice we substitute in the 2 for x and the 0 for x, and we find the difference. So becomes 2 squared is 4 times 2 is 8, and then on this side 0 squared times 2 is 0. So 8 minus 0 is 8. So that's really the difference. On the left hand side we have a definite integral, limits of integration. On the right hand side we have an indefinite integral, no limits of integration, so we have to have plus c. So we're integrating the same function there, but notice on the left hand side a closed interval, on the right hand side an open interval, so we have to use plus c. So hopefully that clears up kind of the difference between what we did in 4.1 and what we are going to do all through 4.4. All we're going to do in 4.4 is evaluate integrals.